Okay, so this is the stat class. This is what, week 8? Yeah, I believe it's week 8. So we're going to go right from the outline here. I'm thinking I may need to use the board. So Ashton, although we can see your pretty face now, do you have the outline with you?
Yes, I do.
So I may be writing some stuff on the board, so I may minimize this, but then it brings that. How do I make sure that there's nothing showing up there? Oh wait, maybe the AV mute? Ashton, can you still hear me? Of course you can. Ashton, are you still there?
Can you hear her?
Did I lose her?
Here.
Uh-oh.
You can't hear her.
Oh, that was interesting. Could you hear me when I was talking before?
Yes.
Okay, I just couldn't hear you. So when I need to use the board, I basically will. Oh, I already brought this up. Okay, so let's just go for it here. So let's start off with a review. There won't be a lot of note-taking in terms of concepts tonight, but it's basically problem solving. So if you look at this first problem on the board, let's just say for the sake of example, we're doing the drug example again. 3 people get a drug, and we're testing, what do we want the dependent variable to be? What should we measure them on? How about, what's that? Well, we got drug and no drug. Let's just say for the sake of example, we're measuring memory. So we give 3 people a drug, and we give 3 people no drug. So this type of design, this is one independent variable. You might call it condition. How many levels? 2 levels, drug and no drug. What's the dependent variable? Not whether or not. It's memory, the memory score, how many words they recall correctly. Now, could we do a t-test on this? We could. One independent variable, 2 levels. If you had a total of 6 people, it would be that independent samples design, right? 3 people get the drug, 3 people don't. But we also learned, I think it was from last week, there's a more general procedure we can use called an analysis of variance. And so I think this is the one we kind of did in class. You guys remember the idea behind the analysis of variance, behind doing an ANOVA? What kind of letter do we compute at the end? An F. You remember the joke? It wasn't for the grade, but the guy who came up with the ANOVA was Fisher. Isn't there a Fisher near Stanton? No. Fishersville. There we go. Has nothing to do with it. Okay, but why not? Sorry, just a little tangential there. So you get an analysis of variance. So the idea is you could look at an F statistic. When you do the F statistic, and once again, I am hoping this is kind of a review, you compute a numerator. Do you remember what the general idea of the numerator was, what we look at? It's the treatment effect. It's called the variance between groups. And it's looking at the treatment effect, the difference between the means. It's the difference between the means. And so you hope that if somebody gets the pill and somebody doesn't, that it's really going to be useful, correct? And so in this case, if you were to even look at this simple example, what is the treatment effect even when you look at this with example number 1? I mean, what are the 2 base numbers that you're going to use here? Yeah, you're going to do all those computations, but just simply, it's kind of the 2 versus the 6, in a way. With this simple example, you hope that the people who got the drug, the mean is much higher. The people who didn't is much lower. So the treatment effect is really the difference between the means, just generally speaking. You were correct, Ashton, in saying the sums of squares and so forth, and we'll go through those details. On the other hand, so you want that numerator to be what, large or small?
Large.
You want that numerator to be large. How about the denominator? What was the general term for the denominator?
The error.
Well, it's the error. It's not, in this case, so much the standard error of the mean. We kind of give it a slightly different term here. Do you remember the different term? We have the variance between groups in the numerator.
The variance within.
Yeah, the variance within groups. And actually, it is very conceptually similar to the standard error of the mean, but it's actually a little bit simpler here, because the variance within groups simply reflects what? Is it good that in example 1 it's a 1, 2, 3 versus example 2, 0, 2, 4?
Yes.
Yeah, it is. The variance within group reflects simply the spread within a group. How do you want the spread within a group to be? Bingo. So I'm hoping this is kind of review, but I didn't want to get ahead of ourselves here. The fact that we have 3 consecutive numbers is good. For the 3 people that got the drug, you'd want their mean to be different, but you'd want the numbers within that group to be pretty close to each other. So no drug versus drug. So we get the variance between groups over the variance within. And actually, we have this ANOVA summary table, which you can look at here. So between groups, once again, how do we want that number to be? The between group sums of squares?
Large.
You want that to be large. Do you guys remember how we actually get a value of 24? Do you remember the little math formula that we used? If you go back and look last week, yeah, you take the number in the group, which is 3, and then you multiply it by the group mean, which in the first group it's 2. You subtract that from the grand mean, which is what? It's the grand mean here. It's 4. So 3 times the quantity 2 minus 4 squared. And then you do the other side, plus 3 times the quantity 6 minus 4 squared. Do you remember doing that for last week? Most people did that in the notes. So that's really reflecting between groups, and that's where you get a 24. So this value, do we want that? We said we want that sums of squares between groups to be large. How do we get degrees of freedom at 1 here?
We do the number of groups and subtracted by 1 because we're using an example of a population.
Exactly. We take the number of groups minus 1. So we have 2 groups, so it's just 1 degree of freedom between groups. How about within group? Do we want the within group sums of squares to be large or small? Small. That number here works out to be 4. Can anybody tell me why that works out to be 4? What do you do for the math?
Do the sum of x minus x squared.
Yeah, you do the sum of each score minus the group mean. So it's 1 minus 2 squared, 2 minus 2 squared, 3 minus 2 squared. Or you can just remember 3 consecutive numbers. The sums of squares is always what?
1.
The sums of squares is always 2 for that.
Oh.
It's the standard deviation that's 1. So you get 2 from that. The sums of squares of 5, 6, and 7. 5 minus 6 squared, 6 minus 6 squared, 7 minus 6 squared. That equals 2. So the sums of squares are 4, and that's good. How does it come up with degrees of freedom within group at 4? Go ahead.
3 in each group, so it's 3 minus 1 plus 3 minus 1.
Bingo. It's 3 in one group, you take 1 away. 3 in the other group, take 1 away. So it's the 2 plus 2 or 4. So you should be able to look at those values and kind of know what we're looking for there. Now, compare that ANOVA screen to what we have on the ANOVA screen below. For example 2. Notice what we have in example 2. No drug, 0, 2, 4. Drug, 4, 6, 8. How are the sums of squares for those two? For the sums of squares between group. So we're looking at sums of squares between group in the second ANOVA table versus the first. They're the same. Why are they the same? Can you see the 24 here and the 24 there? Why are those two the same?
Is it because you still have three consecutive numbers?
Because the three consecutive numbers.
Actually not. It's not because you have three consecutive numbers. It's a good thought. There's another reason. Think of what we were doing up here for the sums of squares between groups. You get what?
Difference between
You get the mean for one group, the mean from the other, and subtract it from the grand mean.
the same.
Oh, it's the same grand mean.
The grand mean is the same, and so are what? The cell means. So the mean of 0, 2, and 4 is the same as the mean of 1, 2, and 3. So the variance between groups, the treatment effect is still what? It's still 24. It's still the same treatment effect. Is that cool? You guys seeing that? So the treatment effect is still the same. So you still got 24 over 1. What is different in this bottom one, though?
That's higher.
Look at the sums of squares within groups for the second example. What number does it give you there?
It gives a higher number.
A higher number, 16. In the top one, it was 4. How come one is a 4 and another one is a 16?
Bigger spread.
It's more spread within group. Is that good or bad? That's bad. The more spread you have within group, the worse it is. The top one, it was 4 because 3 consecutive numbers, 2, 3 consecutive numbers, 2, so it sums of squares 4. You could actually compute the bottom one if you really wanted to. The sums of squares within the no drug group would be an 8. The sums of squares within the drug group would also be an 8, so now we got 16. Degrees of freedom are the same. So let's go to the top case again. In the top case, do you remember what the other term is for mean square? Ashton, what'd you say?
Never mind.
Do you know what the other term is? They actually shouldn't say mean square. What is this analysis called? It's an analysis of variance. When we learned it, I think on week 2, it was kind of the mean sums of squares, but it's variance. So the variance in the top example between group is 24. The variance within groups is a 1. We get an F score of 24. And is that statistically significant? Yeah, the nice thing about these SPSS printouts, it tells you what the exact probability is. So the probability of this is 0.007. How about the bottom case? What happened in the bottom case? How come our F score is lower? What happened in the bottom case?
We have a higher variance within groups.
Yeah, we have a higher variance within groups, so in the bottom case, mean square variance between is 24, good treatment effect, but now the variance within group is 4, you got the F of 6. That was your homework problem, wasn't it? I think I gave that as your homework problem. Notice what it tells you for the p-value. Before, when you looked it up, it was non-significant. What does this tell you? The probability is 0.07. Do you remember what we call that?
Margin.
It's called marginal significance. So you're close, but not quite there. This is marginal significance. Of course, you'd never do a study with just 6 people. Could you write out the F statements from the top and bottom here? The F statement, what would the top F statement be if you had the printout like this? Always good to start out with an F.
1, 4,
F parentheses 1 comma 4 equals
24.
And then what do you put? You could write P less than 0.05, but because you have the exact probability here, it's actually more preferred to actually write out the exact probability. So in this case, you'd actually write out P equals 0.007.
I always wondered when you were supposed to do with the less than or greater than versus the.
You almost always write out the exact probability if you know it. And in almost all real-world examples that you might encounter in the future, you will not do your statistics by hand. A computer will do it. You write it out. There's only one case where you really don't write out the exact one, and that's if it says 0, 0, 0. but we'll
That's
get,
when it's
you write,
0.01, isn't it?
you write less than 001. Did we do an example with that before?
No.
Don't worry about that now. So anyway, you write out P equals 0.007 and you're significant. Real world statement would be what? What would be your real world conclusion?
Drug works.
The drug helps improve memory. Mhm. And in the bottom case, what would you conclude? Well, actually, let's write out the bottom one for example 2. Alpha of what? 1 and 4 equals?
6.
Mhm. Equals 6, comma,
P equals 0.7.
P equals 0.07. And you'd say this is marginally significant. Looks like the drug works, but you would actually say we lack sample size. Actually we did talk about it here. We lack what? Remember? Power. Bingo. We lack power.
So, is that your real world?
Yeah.
statement?
Yeah, probably would be here. Yep.
Okay, wait, so what was the real world statement?
The real world statement is we are marginally significant. It looks like there is an effect of the drug, but our sample size is too low, and we probably lack power.
So the marginal significance was on 0.070,
Yeah.
not 0.007.
Correct. The 0.007 is significant because
Right.
the numbers are so close, we have so few. So yeah. So I would expect that you're feeling comfortable with this. This is a review, but you got that look on your face.
I don't.
Which, so can you ask a question?
I have to really sit down and concentrate very hard to make things click. And sometimes going through it, if I'm not getting something, I'm thinking about what I'm not getting and I miss the rest of it. So,
So-
I'll get it.
Okay.
But I'm not comfortable with it.
So maybe re-listing, oh, that's fair, listening to the acoustics.
I listen to it many times.
Okay. Well, if you want to ask a question at another point, just let me know. This could be, or even now, obviously, you have a specific question here that I can answer. So let's go one more step with this. For the bottom screen here, I put a t-test result. Do you remember what the idea is with the t-test result? We could actually do an independent sample t-test. Do you remember what the relationship is between a t-test and this? Notice our t-score is 2.449.
F is the t-score squared.
So if you take 2.449, anybody got a calculator? You may need, if you've got a calculator or an iPhone or something that you can, we'll be doing a little more math tonight. If you take 2.449 and square it, guess what you get? Wait a second. No, this is wrong.
That's what I was thinking. I was like, wait a minute.
Oh, it was the bottom example, I think.
Yeah, math is not my strong suit, but you get, rounds up to 9 or 6.
Yeah,
Oh, yeah, it's one because
it's the bottom example. T squared equals, oh yeah, you can tell, because look at the sig, 0.07. So T squared equals F. You could do a t-test on this too. So in summary then, hopefully what you've gotten out of this, so let me try to paraphrase so we can make some sense. You do an ANOVA, we want a big treatment effect that's going to make the numerator, the variance between groups, large. Within group, you want the scores within a group to be close together. That's going to lead to a small variance within group. The larger the F score, the lower the probability is, and you tend to be statistically significant.